So what Faraday discovered is now called Faraday's law. It is the fourth of the Maxwell's equations that we are making our way through. We may need to modify one a little bit, but at this point we will have them all. So if we want to put it in sort of plain language, a changing magnetic flux through a wire loop induces an electromotive force in the loop according to we'll just give the equation is that E, a curly E, equals negative d phi b dt. So let's talk about what these things are. So there's the law and the equation, and now let's look over on this side. What is this E? This E stands for, I wrote it up there, electromotive force. It's kind of an old-fashioned word. It basically means, if I had to even define it, we'll define everything, it's the result of something moving charge. It's also called sometimes just EMF for electromotive force, little e, little m, little f. So it really just means anything that causes current to flow. So sometimes you'll have a battery and it gives you a delta V, it gives you a voltage, right? A 9-volt battery gives you a voltage. Sometimes that's called the EMF. The batteries, the chemical reaction of the battery does work to move charge carriers across a potential difference. It's doing work. It's creating an electromotive force pushing the charge carriers. So that term has survived to this day. Eventually we'll be getting rid of the E in this equation. But for now, we'll just think of it as what it is that made the current flow. When we did the demo, you saw the needle shifted. Well, that was measuring the current in all the wire loops. So if we have our loop that looks kind of like that, and we have our B field going through it like this, and that B field is changing in time, then we get a current flowing. And the EMF is what makes that current flow. So EMF is in volts. It's not a current, it's a voltage. But if you want to relate the EMF you induce, the voltage you induce, to the current that flows, then it looks just like Ohm's law. You say the EMF equals the current times the resistance of the loop. Okay? So EMF is like a voltage in a loop. But it's a little different because it's hard to imagine a voltage in a loop. Right? If we have a circuit, then you put a voltage, you have 2 points, and you break the circuit, and you apply a voltage with a battery. But here a voltage is just building up, and a current is flowing. Well, where's the voltage? Where do you apply it? It's hard to think about. If you put it here and here, the current would flow down the side of the loop. One way to think of it is it's like you broke the loop, and you applied a voltage with a battery like that. Okay? But that's why we just call it an EMF. All right, the right-hand side is something we've seen before. Phi b is the magnetic vector flux through, in this case, through the loop. So we define this vector flux just like the electric vector flux. It's the B field dotted with the area vector. Or if you want to do an integral, it'd be the integral of B dot dA. But we have to take this loop, give it an area vector. We'll be doing this more later. And then we can define these two things. So if your magnetic vector flux changes in time, that induces the little electrical effect that we saw. And that's really what Faraday discovered. You can't just put a magnet near a bunch of loops. You have to have the magnet move. You have to have the magnetic field change.